Modern industrial production runs on automation, but blurring the lines between plant-level control and network-level monitoring introduces dangerous latency into systems handling highly volatile materials. Confusing these architectures leads directly to hardware failure and catastrophic safety risks. When engineers design these massive operations, they rely on two heavyweights of industrial automation: DCS, or Distributed Control System, and SCADA, which stands for Supervisory Control and Data Acquisition. Walk into a control room for either system, and they look identical to the untrained eye. Operators sit in front of multi-monitor arrays, reading sensor data, acknowledging alarms, and manipulating field equipment through graphic interfaces. Because they look the same, companies often try to force one system to do the job of the other. Attempting to use a SCADA system to manage the microsecond pressure changes of a chemical reactor will lead to a catastrophic blowout. Conversely, trying to stretch a hardwired DCS architecture across a 500-mile gas pipeline is financially and physically impossible. These two systems are not competitors. They are highly specialized tools dictated entirely by the geographic scale of your operation and the processing speed required to keep it safe. A distributed control system operates strictly inside the fence. It is purpose-built to manage complex, continuous processes contained within a single physical footprint, like an oil refinery, a pharmaceutical plant, or a paper mill. Instead of relying on a single, distant computer to make all the decisions, a DCS decentralizes its brain. It places multiple physical controllers right next to the actual field equipment they are managing. The process starts with input-output modules. These act as high-speed translators. They capture raw analog data, like voltage or resistance from a temperature sensor, and instantly converts it into a digital signal that the local controller can read. Because that controller is sitting right next to the valve, it operates in a closed loop. It reads the data, calculates the required adjustment, and sends a command back to the valve immediately. It does all of this locally, without ever asking a central server for permission. That localized loop delivers incredible speed. A DCS reacts to process variations in milliseconds. When you are mixing highly reactive chemicals, that fraction of a second is the difference between a stable batch and a thermal runaway. To guarantee that speed never falters, DCS hardware is heavily redundant. You will find backup controllers, redundant servers, and overlapping network switches specifically engineered to eliminate any single point of failure within that hazardous environment. If a pharmaceutical reactor requires a specific flow rate to maintain temperature, the local DCS controller makes hundreds of micro adjustments per minute to hold those precise microsecond tolerances perfectly flat. The trade-off for this speed is physical limitation. A DCS requires a massive hardwired local plant network of copper and fiber optics to carry those heavy data loads continuously. You cannot run that kind of infrastructure across a state line. By design, a DCS deliberately sacrifices geographical reach to guarantee localized, ultra-reliable, high-speed process safety. Once you move outside the fence, the engineering math changes. Instead of a single dense facility, you are dealing with assets sprawling out over hundreds of miles of remote terrain. This is where SCADA takes over. It is an eye-in-the-sky monitoring system built specifically to supervise massive, decentralized infrastructure, like regional electrical grids, cross-country pipelines, and municipal water treatment networks. Instead of dense racks of local controllers, SCADA relies on remote terminal units, or RTUs. These ruggedized computers sit out in the field at distant pump stations and electrical substations, quietly collecting data from local sensors. To get that data back to operators, SCADA leans on wide-area networks. It utilizes radio waves, cellular, and satellite telemetry to bridge vast physical distances and connect those scattered RTUs to one central control room. You cannot maintain a microsecond continuous loop over a satellite connection. Instead, SCADA systems collect data by polling them periodically, or waiting for an RTU to trigger an event-based alarm. Updates register in seconds or minutes, not milliseconds. Because of this delay, SCADA utilizes supervisory, open-loop control. Operators use the interface to send high-level commands, like telling a reservoir pump 50 miles away to turn on, but they leave the continuous micro-adjustments to the equipment on site. Operating over these vast distances introduces vulnerability to connection drops. If a radio signal fails in a storm, the central SCADA server goes blind. Therefore, the local RTUs and PLCs out in the field are programmed to handle their own basic failsafes until the connection is restored. SCADA trades away real-time, microsecond control. In exchange, it achieves highly cost-effective visibility and data acquisition across massive geographic areas. This infographic directly compares the technical footprints of both architectures, mapping out exactly where each system belongs. Look at their foundational purposes. DCS is built entirely around plant-level control, driving the continuous actions of a contained facility. SCADA is built for remote monitoring, supervising assets from a distance. This dictates their physical layout. DCS utilizes a web of local controllers reporting to a process room on site. SCADA centralizes everything into a single hub that pulls telemetry from scattered geographic regions. Observe the difference in data speed requirements. A DCS guarantees millisecond response times to keep volatile processes stable. SCADA prioritizes alarm logging and historical data collection to track trends over time. You can see the communication backbone driving those speeds. DCS relies on a heavy, isolated local plant network. SCADA routes its data through internet clouds and wide area telemetry. These mechanics dictate the industries that rely on them. You need a DCS for precise chemical batch processing. You need SCADA to monitor water pump stations and miles of pipeline. The human operator's role shifts entirely based on the system. A DCS operator is actively flying the plane, managing complex process variables. A SCADA operator is acting as air traffic control, monitoring the map and making high-level routing decisions. If you need to execute fast, precise physical actions safely, you deploy a DCS. If you need to coordinate visibility across a sprawling network, you deploy SCADA. Software vendors today often market platforms that claim to blur these lines, offering SCADA systems with control capabilities or DCS platforms with cloud monitoring. But underneath the interface, the absolute physics of network speed and physical scale remain firmly in place. In modern industrial operations, large corporations don't choose between the two. They stack them hierarchically. At the base layer, individual manufacturing plants use their own dedicated, hardwired DCS systems to maintain safe, high-speed, closed-loop control of their localized equipment. Those local DCS systems then act like massive field devices themselves, feeding their aggregated, filtered data upward into a global SCADA layer. By integrating them, corporate headquarters gains the geographic SCADA visibility needed to monitor production across a dozen global facilities at once, while fully trusting the local DCS layers to maintain safe pressure and temperature tolerances on site. Bridging those isolated local plants into a wide area network creates a severe engineering challenge. Pushing DCS data to the cloud safely requires sophisticated, zero-trust cybersecurity protocols to ensure a remote connection cannot physically manipulate local valves. DCS controls the process. SCADA coordinates the landscape. Recognizing the rigid boundaries of both is how you build an automation framework that scales without sacrificing safety. To dig deeper into system integration, advanced automation hardware, and compliance standards for your specific facility, check out the training workshops and resources linked in the description below.